Nicolas,
All right, so welcome everybody to the Master's Defense of Lucas Rouhier. I got to meet Lucas when he took one or two of my graduate classes. I think you took both, right? Image processing and emergent biomedical technology. So it was really nice to have him in the class. And, you know, it seems like we had quite a lot of interaction back then. And he's learned quite a lot about image processing in the years since. And I think this thesis shows that. Today, we're going to be talking about his master's project called Prognosis for Degenerative Cervical Myelopathy, a computer learning approach on the AO Spine database. Julien Cohen-Haddad is the supervisor and Samuel Kaduri is on the jury. We all reviewed Lucas's thesis and we will have a discussion about it after the presentation. Now we're going to sit for about 20, maybe 30 minutes, Lucas? Is that the target?
Yeah, 20, 30 minutes.
To hear the introduction to his thesis, and afterwards we'll have a discussion about it. So thank you all for joining. And unless there's any other comments or procedural checkboxes we need to do, I'd encourage Lucas to start sharing the screen.
Okay, thank you very much for the introduction. So I'm going to start sharing my screen. Just give me a sec. Up. On to presentation mode. So, hello everyone. So, thank you for the introduction. I am going to talk about computer learning for post-surgery prognosis for patients suffering from DCM, which is degenerative cervical myelopathy. And this study was done on the AO Spine database. So, just a bit about this presentation. So, it will start off with a bit of context about with the anatomical consideration that is needed for a study such as this one, and a bit about the condition itself before moving on to some generality about machine learning and deep learning usage. After the objective, we'll move on to the methodology and the material with a short data presentation and then a detail about the approaches that was done on this study. So that results and conclude, we will see the results and conclude on our work. So about the anatomical consideration that you need to have for a study such as this one, is that the spinal cord is a highly sensitive organ with tremendous importance as it pertains to the nervous system and connect the brain to the limbs. There are multiple pathways in the spinal cord that exist, and you can see that they can have different roles. So there is some ascending and descending pathways. This is relevant because it will explain a huge case-by-case difference for patients suffering from spinal cord injuries in general, and in our cases, because the DCM is a spinal cord condition. It's a condition that affects the spinal cord. And the condition itself occurs as a result of the spinal cord compression of the spinal cord by a vertebral body, and can have multiple causes, as you can see here on the image on the right. These multiple causes explain a high patient intervariability in the treatment strategy and in the diagnosis, which can be pretty long. It can take up to 2 years according to recent studies, which is problematic because the condition is degenerative and will get worse as time goes by. It affects the patient's sensory motor skills. So in the beginning, it might be some numbness in the end and some clumsiness, and it can degenerate into paraplegia and tetraplegia if left untreated. So how do we treat it? We currently treat it with decompressive surgery, which is more of a generic word because it regroups a certain number of approaches. But this surgery is only successful in 40% of the cases. And a surgery is considered successful when the patient's sensory motor skills improve significantly after the surgery. We will get back later about the significance of how do we measure the significance of the improvement. The surgery involves multiple risks, for example, C5 palsy, which can be pretty bad. And of course, this is linked to the fact that we are dealing with an operation very close to the spinal cord. So what is important in that case is that if we could establish a good post-surgery prognosis, we could avoid that patients go through surgery if it's not needed. Unfortunately, the current post-surgery prognosis is not really efficient, so the surgery is the default operation, is the default next step after the diagnosis. Different types of surgery can be performed. So there are two main approaches, which are anterior and posteriors, and there are four main different types of surgery that are performed in the different cases. And it is more of a case-by-case selection by the practitioner, which increase the fact that it's going to be complicated to predict the patient state because it can depend on the surgery and on how the surgery goes. So deep learning and machine learning are two methods of computer learning that have gained traction in the last decades. And their main application and then classification, localization, and segmentation. We are more interested in the classification part because our problem will be to classify if the patient needs surgery or not. But just to explain a bit about it, so localization is when the algorithm will try to process images to find the coordinate of an object. For example, here, it has found where the liver is located and it has classified it as the liver. Same goes for the spine. Then the last application that is mostly used in biomedical is the segmentation. So on this image, you can see the edge of the segmentation. We only show the edge because it's better for visual purposes, but a real segmentation will have this whole shape field, yellow. And you can see that the edge on the segmentation is very sharp around and very close to the actual boundary of the organs. So the objective for these studies was to develop the model based on artificial intelligence and computer learning, so that can be used in patient prognosis and treatment of DCM. And the sub-objective was to establish the efficiency of using MRI in conjunction with clinical data, providing better results in treatment and prognosis, and to establish the post-operative prognostic model for DCM. So a bit about our data. The AOSPINE database is composed of two types of data, mainly. So the first one is clinical data, which is a table that contains information about the patient. There are some medical information, for example, comorbidities, such as if the patient has a heart condition or diabetes, because this can be relevant to his rehabilitation process after the surgery. There are some general information, such as age, sex, marital status, stuff like that, to see if there can be any correlation. And then we have another part in this tabular data, which is the medical evaluation of the condition. So we have a pre-surgery evaluation on different scale and a post-surgery evaluation on different scale at different time points, so 6, 12, and 24 months after. We are using the MGOA scale because it seems to be the more relevant. So MGOA is the Modified Japanese Orthopedic Association scale, which allows us to separate the patients into functional classes. So if the difference in MGOA before and after the surgery is greater than 2, then we consider this a successful surgery. If not, it is an unsuccessful surgery. The second part of this data are T1 and T2 weighted pre-surgery MR image. So here you can see T2 sagittal image that come from the dataset. We are using T2 weighted in this image because it's easier to see the spinal cord in those. And the green arrows point to the compression area. So as you can see, it can happen at different level and from different sides, which explains a huge patient intervariability. So in this study, there were 769 enrolled patients. And of those, 476 completed 3 follow-ups of 6, 12, and 24 months. 246 of these 476 had a good T1 and T2 image, and 158 had a good axial images, which is an axial images with a resolution above 1 millimeter square in the APLR plan. and visibility on the compression area. Just before we move on to our approaches, this is the general workflow that we will use for every approaches, which is we take the data and take it through a cleaning part where we will remove what is unwanted or what is totally incoherent with what we expected. Then we go through a pre-processing phase where we try to normalize our data, remove some unwanted feature, and try to get everything ready to fit to the model that we will select and implement, and so that we can evaluate it. Once we have evaluated it, we can optimize the model by either selecting a different model, of course, if the results are totally wrong, or modify its implementation, for example, modify the parameters that pertain to the model. So for the first approach, which is an easier one, in fact, which is why we started with that, is to start by exploiting clinical data. It is a bit easier because the common machine learning method are already implemented and mostly tested, and it already exists some literature about it now with this problem that appears during the first 6 months of my master thesis. But for pre-processing, we might want to remove unwanted features that might cause overfitting. So the unwanted features would be, for example, admission date into the study, surgery date, because it's not supposed to be relevant to our problem. And overfitting, in fact, is the process, is an important issue in machine learning. It's when a model learns the specific of a subject and not why the subject is either a 0 or a 1, because we are talking about classification. So 2 studies already exploited some clinical data with this approach using 2 different algorithms. So the first one was random forest, and the second one was boosting. So the boosting algorithm they used is actually a general boosting method, which is why we call them boosting. But they both used a subset of clinical data containing some information about the operation, which is a bit surprising because we are trying to make a pre-surgery prognosis, so we won't have any information about the operation. We will see in the results what happens when we remove those information. For our study, we decided to compare random forest to XGBoost because it seemed to be a pretty efficient algorithm in cases such as this one, as it has been seen in my biomedical application. About our algorithm, what is interesting is that we have 2 different types of construction. They are both ensembling algorithm, which means that, in fact, there are a bunch of submodels that vote for an output, and the majority decide what is the model's, just the top model output. But for random forest, for example, you can see that all trees are already there. So for example, we have 3 trees. So, and we will modify the weights of the vote of each tree. Whereas for XGBoost, we will actually build the tree sequentially to try and reduce the error. So we'll add new trees to reduce the error of the voting process. And here for random forest, for example, we diminish the weights of the votes of the trees that is wrong. So we had some pretty good results with that, but as I mentioned, we wanted to use the image to check if it was efficient to use the image as well as the clinical data, because the current prognosis relies on the state of the compression, which is obtained through MR images. And the exploitation of the image could provide new information and shed some light on the clinical data. Deep learning is now coming to be a common method to find patterns in images, especially since the most machine learning method will require feature extraction, which can be pretty dicey if the images are not rated by an expert. And we focused on 2 main classification methods, which is the ResNet and Inception Becat, V4, sorry, which are 2 models that emerged in the last 5 years that are pretty good at classification. And we use the supervised methods, so which means that we will feed the network the image and the ground truth, so the answer that is expected. So he can compute his loss and modify its weights accordingly to try and reduce this. So our image were preprocessed using the spinal cord toolbox. So basically we took our original image, resampled it so that they all had the same physical distance. We cropped them so that we try to reduce the number of external information to try and keep only the information that pertain to the compression area. Then we resample them to try and make them more precise and maybe increase the network and the network performance. For the processing, we did the first test with a ResNet and only T2 images, which was not working well. So we tried a different approach because there seemed to be a correlation between the hyperintensity in T1 and hyperintensity in T2 and a successful surgery that was discovered recently. And therefore, we try to move on with a multi-input network that will allow us to have T2 and T1 images at the same time to see if that could improve the score. And since the clinical data alone provided interesting scores, when that started to not work well, we tried to add the clinical data information. Unfortunately, it did not go very well. So we tried to go back to the feature extraction approach that we were trying to avoid. And the rationale for that is that it exists some studies on using MR diffusion imaging that have unmatched success for post-surgery prediction in our cases. Fortunately, we don't have diffusion imaging in this database. But in any case, it was interesting because the image exploitation was not done in any previous studies using the AOSpine database. But of course, the downside is that we had a restrained number of subjects. So we had a pipeline for feature extraction, which was we take our original image, put it through actually a deep learning model in spinal cord toolbox that will give us the spinal cord segmentation. With this spinal cord segmentation and the original image, we can perform some vertebral labeling. And this will give us the localization of the disc. And with the localization of the disc and the segmentation, we can register this image to the atlas. After that, we can take some information from the atlas to add to our clinical data and feed it to a machine learning model. So a bit about our optimization that was used here. So first, there is a manual process, which is to monitor the features of importance. So we can go back to processing and create another approach with different features. Then there are the hyperparameters. So for example, this would be the number of trees in a random forest or the batch size for a deep learning model. To optimize these hyperparameters, you can do it manually, or you can go through automatic process. So one of these processes is grid search. And this is pretty commonly used, but it allows you, for example, if you have two parameters with three values that you want to test, it will test all the combination of these three values for both parameters. So for example, parameter 1 value 1 with parameter 2 value 1, parameter 1 value 2 with parameter 2 value 1, etc., etc. It is mostly used right now for deep learning because there is not a good implementation that I have seen of the Bayesian optimization process for deep learning model. Bayesian optimization relies on a probabilistic model, which is great because it allows you to actually have a range of continuous value, while grid search is only discrete value. So of course, all combinations are tested, but you have to define what combination can be tested in the beginning. Bayesian optimization allows you to bypass that. It will create a probabilistic model of the output of the network and try to optimize the hyperparameters with that to try and determine which parameters will be the best. And we use that on the more machine learning classic model. About our evaluation method, so for the deep learning, we mostly focused on a train test division with 80% of the dataset for training and 20% for testing. Whereas for machine learning, we used a tenfold cross-validation method. We use that because the training is a bit time-consuming for deep learning, so this might take a while to do some cross-validation on it. And how does cross-validation work? So basically, you divide your data in a certain number of folds. Here there is 4, and you train on all of them -1, and you test on the last one, and then you permute that. You permute the fold that is tested, so that you can move on. And in the end, you have tested 4 times, so your accuracy or the score you obtain is a bit more robust and reliable. Speaking of scores, these are the 2 metrics that we use to monitor our model. First, there is the accuracy, which is sort of a binary evaluation. So for example, it's just measure if the network output 1 when the answer was supposed to be 1. And of course, a higher score means a better performance. And then we used also the area under the curve when it seemed relevant. So this is built with true positive rates, and which is the sensitivity, as you can see here, false positive rate, which is the specificity, as you can see here. This seemed relevant because we might want to move to a more specific or a more sensitive network, depending on the case, especially in biomedical. So this could be interesting to look at. So the first result that I wanted to show you is the one that explains why we move on with XGBoost and random forest and not other algorithm. So in this result, you can see that XGBoost and random forest seems to perform better on a 10-fold cross-validation, which was done twice. And this is the box plot of the result. Bagging methods are a bit different, so I wanted to try it to see if it was better than the ensembling algorithm. And extra trees is a derived of random forests, so I wanted to see if extra trees could be better than random forest at the time. KNN is k-nearest neighbor, which is an unsupervised method, which is the only one that was tested. And an unsupervised method actually didn't use the ground truth to implement the loss, but just try to gather data by similarity. So the best performing algorithm are XGBoost and random forest, due to the fact that they seem to have a lower STD and a higher median score, even though the baseline was 63%. So for this baseline result that were obtained with the first set of clinical data that contains the operation level and the duration of the operation, are actually very close to what was obtained in the previous study. So this is good because it speaks to the reproducibility of what we are doing right now. And so the accuracy was 70, so we had an increase of roughly 7%. This is the same information, but without actually the operation data. And we can see that removing the operation data does not seem to hurt the model too much, to hinder its performance, which is great because it speaks to the fact that we are moving toward a real pre-surgery prognosis. So a bit about our optimization process. We can see here that it has some pretty good results, and it was not tested previously, so this is some interesting information, that the Bayesian optimization is a reliable tool to improve our model performance in that case, because the improvement was significant for both models. Here you only see the result for XGBoost, but the accuracy improved by 2.5%, which is pretty great. So we now have closer to a 10% improvement. The last result of this series is the feature extraction one, so from the third approach. And the baseline was a bit different here because it was at 57%, because we had less subjects, so we had a different baseline, of course. And there is a 9% improvement with random forest, which was the best performing one at this time. XGBoost was actually closer to 65%. Well, this one is 65.6. And this is a 9% improvement. So we show it is an improvement close to what we can see with the model with all the subjects. but it is not significant as to the difference without using this data and with this data. So, for the deep learning, the results were mostly unsuccessful because the model were either overfitting or didn't provide some significant improvements of the accuracy score compared to the baseline. So in summary, we have tried new approaches to establish prognosis, and state-of-the-art deep learning does not seem to be the best method right now. So maybe focusing on machine learning on clinical data and extracted features might be a better approach, even though we can provide only a limited improvement at the time. And what is important also is that the operation information does not seem relevant, even though it has been kept in previous literature. The semi-automatic pipeline that could be established from here on out to exploit the images can be interesting for future research, as I will mention later. And what I mean by semi-automatic is, of course, the fact that it might need some manual correction at some steps in the way, especially for segmentation and for delocalization. So the consideration that you need to have regarding to this study is that we still have a limited amount of data, which is problematic when you are using machine learning and deep learning, because these are example method, which means that they are only as strong as the data that you can feed them. And comparison with new technology can be important, especially since right now the research is going towards diffusion imaging in MR research, of course. And the consistency in the operation technique and following treatment is crucial, I think, because it will remove a random factor, sort of. Because even though the operation can only be of different type, it is still depending on the practitioner experience and what you want to do in a case-by-case basis. So as I mentioned, some patients' info about post-surgical treatment could help, because the rehabilitation process could be improved by a post-surgical treatment. And maybe not using the 24 months mark could be useful, so that we could include more patients who have not completed the study but have been to the 6 months or 12 months follow-up. A bit about the model in deep learning is that, of course, we are not tested all the model in deep learning, but the absence of significant improvement lets think that maybe it's not the way to go. Of course, moving toward maybe a less complex model could be useful, because overfitting is often a sign of using a model too complex. For the atlas and the preprocessing, there was a non-expert rating of the automatic segmentation, because as much as I have worked on that, I am not an expert on the segmentation of the spinal cord and on the disk, so I might have made a few mistakes. And the problem for the atlas registration is that the shape cannot be used as reference due to the compression, and so a sort of rotation could factor in, because the symmetry is not great in all images, because sometimes the left part of the spine is crushed and not the right part. Of course, an atlas would still have limited value compared to DTI image, but it could still be interesting, because the previous study only used an atlas with 8 labels, and the atlas that we used here used 50 labels, so 50 different regions of interest within the spinal cord. And it could be relevant to use that in future study. So of course, new research promotes the use of diffusion image to monitor its condition, which seems pretty relevant comparing the result that we have and the results that have been obtained in the literature. We could move on to a model focusing on a single practitioner or a single method to see if it could improve results, to see if that is really depending on the operation type. And finally, one of the new technology that have emerged nowadays is the explainable AI, which aims at understanding the reasoning of any algorithm and could help us see connection between features and the result that we have. So I would like to thank the whole team from the lab for their help during the last 2 years. And of course, I would like to Thanks Drs. Filling and Michael Weber for sharing with me the AOSPINE database, and the Dr. Hagba for his input on the work and help with the database to begin with. These are the reference. If you have any questions, please feel free to ask them.